Hello, we are Group 8 and we will be determining the charge on a balloon. So here's our problem. We have two balloons and they both have a given charge, and we need to determine the exact values of these charges. So for our model, we have a basic system schema showing both charges Q1 and Q2, the earth, and the ring stand. The stand applies a contact tension force to both Q1 and Q2, the earth applies a gravitational force to Q1 and Q2, and both Q1 and Q2 apply a Coulomb force to each other. This force is of most interest to us in this experiment. Our free body diagram, which you can see in the lower left of our slide, shows these interactions and the directions in which they would be working in. Now, assuming each ball in the free body diagram is a point charge, you can see that each experiences tension, gravitational, and electrical forces. Also, notice that the components of the tension force are equal to the other forces present. Our experimental design is fairly interesting. We hung two balloons from strings of equal lengths from the same point on our meter stick, which was supported by a ring stand hanging off the side of the table. We charged each balloon by giving it one quick rub through my hair on all sides to ensure an equal charge. From there, we set the balloons close enough together and then released them. Once they came to a full stop, we measured the distance between them to get our R value. This is one of the key variables in the Coulomb equation.
Recall how the key points of the free body diagram included tension, gravitational, and Coulomb forces. Gravitational forces depended on mass, so we measured each balloon at 3.5 grams. For tension forces, we made sure both strings were 43 centimeters to keep things constant. And for Coulomb forces, we were interested in distance, R, to measure those forces. For trial 1, our distance was 22 centimeters. For trial 2, our distance was 31 centimeters. In trial 3, our distance was 27 centimeters. Both mass and the string length were constant for each trial.
With this data collected, we were now ready to calculate the charges on the balloons. The first step in doing so was calculating the tension forces, primarily the horizontal tension force, in which we needed to determine theta. Since the masses of the balloons were the same, 3.5 grams, and the length of the connecting strings were the same, 43 centimeters, we were able to treat this setup as an isosceles triangle, in which the bottom base was r over 2 and the hypotenuse is 43. From this, we were able to use the law of cosines to determine the angle theta. The angle for trial 1 was 75.17 degrees, for trial 2 it was 68.87 degrees, and for trial 3 it was 72.54 degrees. We took the averages of both the distances between the two balloons and the angles for all three trials. The averages were r equals 26.6 repeating centimeters, and for theta it was 71.90 degrees. With all of that said, we can now put everything together. As you can see in the free body, the magnitude of the force of gravity is equal to the magnitude of the vertical component of the tension. As you can see in the first line, this value is 0.0343 newtons. Using this value, alongside the law of tangents, as well as the average angles that we determined, we were able to calculate the horizontal component of the tension force, which is equal to the magnitude of the Coulomb force. Using the average value of R, and with the Coulomb constant at 9 times 10 to the 9, we are able to determine the charge of both balloons, which is plus or minus 2.98 times 10 to the negative 7 coulombs. To determine the exact sign of the charge of the balloons, we would have had to see how they behaved when interacting with an object of a known charge. In any case, dividing our Q value by 1.6 times 10 to the negative 19, the Coulomb charge of an electron, allowed us to estimate that approximately 1.86 times 10 to the 12 electrons were transferred in the charging process.
Our sources of error likely stem from three key areas: charging consistency, air resistance, and friction between the string and stand. Charging consistency would possibly be unequal, as rubbing a balloon on a lab mate's hair isn't the most consistent way of going about it, as timing isn't perfect. Air resistance and friction both prevent the balloons from pushing or repelling each other as far as they possibly could. So these are where our sources of error likely stem from that alter our found value.
So although our model didn't account for forces of friction, air resistance, and volume, recall that we assumed our balloons would behave as if they were point charges. We felt that our model, based on the most significant interactions, i.e. Coulomb forces, gravity, and tension, was sufficiently accurate.